The moon deceives us every single night. We have looked at it for thousands of years, admired its light, and read poems about the sea of tranquility and the sea of serenity. Yet we see only one side of it, always the same one. The other half of our satellite has been hidden from human eyes since the very moment our first ancestor lifted their head toward the stars. Why? Because the moon is locked in synchronous rotation. It rotates around its axis in exactly the same amount of time it takes to complete one orbit around the Earth. 27 days one way, 27 days the other. Throughout all of human history, we could not peek behind this curtain. We built myths, composed legends, and fantasized about what lay there. When we finally took a look, reality turned out to be stranger than any fiction. The far side of the moon is not just a copy of the visible one. It is a completely different world. A world without seas, without the familiar spots that form the face of the man in the moon. There are constant scars, craters upon craters. It is the most ancient surface in the solar system, remembering the times when planets were still forming from debris. There is a giant wound inflicted by an impact that nearly split the moon in half. There is eternal darkness and ice older than dinosaurs. There is a silence that exists nowhere else in the vicinity of Earth. And there, perhaps, lies the future of humanity. Before we dive into this story, subscribe to the channel and give it a like. Every week we reveal secrets of space that textbooks stay silent about. Do not miss the next episode. When people first saw the moon through a telescope, they decided that the dark spots on its surface were seas, real oceans. Galileo Galilei in 1609 examined these smooth lowlands and gave them romantic names: Sea of Rains, Ocean of Storms, Sea of Serenity. Of course, there was no water there. It is frozen lava, basaltic plains that flooded giant impact basins billions of years ago. But the names stuck, and these seas became the most recognizable feature of the moon. They are the ones that form the very pattern that some see as a face, others as a rabbit, and others as a woman knitting. Cultures all over the world looked at the moon and saw their own things, yet everyone saw the same thing because the moon is always turned toward us with one side. What about the other side? For centuries, no one knew. There was no way to find out. One could build guesses, put forward hypotheses, but it was impossible to verify them. Some astronomers assumed that the far side was an exact copy of the visible one. Why would the moon be asymmetrical? Others believed there might be an atmosphere there. After all, since we cannot see it, maybe it is hiding right there. Still others fantasized about civilizations hiding from our eyes. But all these were merely conjectures. The truth remained beyond the event horizon, in a literal sense, beyond the lunar horizon. The problem with synchronous rotation is that it is not an anomaly. It is the norm for large satellites. Most moons in the solar system are locked in the same dance with their planets. The reason is tidal forces. Earth, with its gravity, deforms the moon, creating tidal bulges on its surface. These bulges, in turn, create a torque that gradually slows the satellite's rotation until it synchronizes with its orbital period. The process takes millions of years, but the result is inevitable. A gravitational lock. The moon fell into this trap approximately 4 billion years ago, shortly after its formation. Since then, humanity, which appeared much later, has looked at only one of its hemispheres. Of course, libration, a slight wobbling of the moon due to the ellipticity of its orbit and the tilt of its axis, allows us to see slightly more than half of the surface, about 59%. But the remaining 41% was absolutely inaccessible. This is not just an area of ignorance. It is a hole in our maps of reality. A white spot the size of Australia hanging 380,000 kilometers above our heads. And this hole gave birth to myths. In the 19th century, the first science fiction novels about the moon appeared. Jules Verne, in the book From the Earth to the Moon, sent his characters to the satellite, but even he did not describe the far side. There simply were no data. Herbert Wells, in The First Men in the Moon, populated it with underground civilizations. Since the surface is barren, perhaps life went deep inside. Fantasy filled the void. In the 20th century, when the space race began, this void became even more intriguing. The far side of the moon turned into a symbol of the unattainable, a metaphor for everything hidden and unknown. The Soviet Union and the United States fought for space. The first satellite, the first man in space, the first spacewalk. The Soviet Union was pulling ahead, but the far side of the moon remained an impregnable fortress for both superpowers. To see it, one had to send a craft that would fly around the moon, photograph the invisible half, and transmit the images to Earth. It sounds simple, but in the 1950s, it was on the verge of the impossible. Precise navigation, a powerful rocket, a photography system that could work in a vacuum, and a communication channel capable of transmitting data across hundreds of thousands of kilometers of cosmic void were needed. The Soviet Union decided to be the first. On October 3, 1959, the Vostok L rocket launched from the Baikonur Cosmodrome, carrying the Luna 3 station. It was a small machine weighing a bit more than 278 kilograms, packed with cameras, transmitters, and an orientation system. Its task was to fly around the moon, take pictures of the far side, and return them to Earth. No one had done this before. No one even knew if it would work. The trajectory was calculated so that the station would pass behind the moon at a minimum distance and then return toward Earth to transmit the data. No landing, no complex maneuvers in orbit. Just fly by, shoot, and return. But even this was a grand achievement. On October 6, Luna 3 reached the vicinity of the satellite. Shooting began. The station carried two cameras, one wide-angle, the other with a long focus. Film, real photographic film, like in the ordinary cameras of that time, but not simple. Special film, resistant to radiation and the temperature fluctuations of space. The cameras clicked frame after frame, capturing a surface that no one had ever seen before. Then the film was automatically developed right on board the station. A chemical process in zero gravity under vacuum conditions. A technology that seems crazy even now. After development, the film was scanned, and the images were transmitted to Earth via a radio channel. Slowly, line by line. Every pixel was a grain of information that pushed through hundreds of thousands of kilometers of space. When the first images arrived at the Mission Control Center, silence fell. People looked at the screens and could not believe their eyes. The far side of the moon looked nothing like the visible one. No seas, almost no dark spots. Instead, there was a continuous scattering of craters, as if someone had taken the surface and systematically beaten it with a hammer billions of times. Craters upon even more ancient craters. A light, pitted, scarred land. It was a revelation. Why is one side flooded with lava, while the other looks like a battlefield where the battle never ended? The images were grainy and of low resolution. The technologies of 1950 did not allow for more. But even on these blurry frames, it was visible. The moon is asymmetrical. It has two sides, two faces, two different stories. And this asymmetry demanded an explanation. Soviet scientists rejoiced. They were the first to see what had been hidden from humanity since the beginning of time. They compiled the first map of the far side and gave names to the largest craters. The Sea of Moscow is the only dark spot on the far side, tiny compared to the seas of the visible hemisphere. Tsiolkovsky crater is a giant depression with a dark bottom, named after the father of cosmonautics. Giordano Bruno crater is fresh and bright, with rays of ejecta spreading in all directions. But the main discovery was not in the names. The main thing was that the moon turned out to be a mystery. Why is the visible side covered with seas while the far side is not? The first hypothesis that came to scientists' minds was the difference in bombardment. Perhaps the visible side received more impacts from large asteroids that pierced the crust and released lava, but this explained nothing. The far side is covered with craters even more heavily. There are more traces of impacts there, not fewer. This means it is not about the number of bombardments. The second hypothesis was crust thickness. What if the crust on the far side is thicker, and the magma simply could not break through to the surface? This sounded logical. Lava fills lowlands only when it can escape from the depths. If the crust is too thick, it works like a lid on a pot, keeping the pressure inside. But where did such a difference in thickness come from? The moon formed as a single whole. Why should one half be thicker than the other? The third hypothesis was Earth's gravity. The visible side is always directed toward our planet. Earth's tidal forces constantly affect it, deforming and heating it. Perhaps this heating made the crust of the visible side thinner and more fragile. Maybe that is precisely why magma penetrated the surface more easily. This explanation seemed convincing, but the details did not add up. Tidal heating exists, but it is not enough to explain such a radical difference. The fourth idea was composition. What if the visible and far sides initially formed from different materials? Perhaps during the formation of the moon, and it was most likely born from debris after Earth's collision with a protoplanet the size of Mars, the material was distributed unevenly. Heavier elements settled on one side, lighter ones on the other. And this difference in composition determined where the crust would be thin and where it would be thick, where the lava would break through and where it would not. Each of these hypotheses had supporters. Scientists argued, built models, and calculated, but there was no exact answer, and that is because data were scarce. The images from Luna 3 opened up the far side but did not reveal its secrets. For real understanding, new missions were needed. More detailed maps, soil samples, and seismic data. The space race of the 1960s provided all this. The era of lunar programs saw the Soviet Union send automatic stations one after another. Luna 9 made the first soft landing. Luna 16 delivered soil to Earth. Lunokhod 1 traveled kilometers across the surface, studying regolith and rocks. The United States launched the Apollo program, manned expeditions that changed history. Neil Armstrong stepped onto the moon on July 20, 1969. Others followed. In total, 12 people walked on the moon. They collected samples, installed instruments, and took photographs, but all of them landed on the visible side. The far side remained inaccessible. It was impossible to land there because there was no direct radio communication with Earth. The moon's horizon blocked the signal. To work on the far side, a relay satellite was needed to transmit commands and data. Such technology would appear later, but orbital craft studied the far side. Lunar Orbiter, a series of American probes in the 60s, took thousands of detailed images. Maps became more accurate, and with each new image, the asymmetry looked even stranger. The visible side has about 30% of its surface covered by lava seas. The far side has less than 2%, a giant difference. Why? The answer began to clear up when scientists studied the samples brought back by the Apollos. Lunar basalt, the frozen lava of the seas, turned out to be younger than the highlands. The seas formed approximately from 3 to 3.5 billion years ago. The highlands are older, 4 to 4.5 billion years. That is, first the moon was entirely covered with an ancient light crust, then giant impacts pierced this crust, creating basins. And then, hundreds of millions of years later, these basins were filled with lava that rose from the depths. Volcanic activity, but not random. It was directed. Magma flowed where the crust was thinner, where pressure could break it. Orbital measurements confirmed that the crust on the far side is indeed thicker, averaging 50 kilometers. On the visible side, it is 30. a difference of 20 kilometers. This is a huge value on the scale of a celestial body with a diameter of 3,500 kilometers. 20 extra kilometers of rock is a barrier that magma could not overcome. Impacts created basins on the far side as well, but lava did not fill them. It got stuck under the crust, cooled, crystallized, and never reached the surface. But where did this difference in thickness come from? This is where the most interesting part begins. The modern theory of moon formation states, our satellite was born from a catastrophe. Approximately 4.5 billion years ago, when Earth was still young and red-hot, a protoplanet the size of Mars crashed into it. The impact was monstrous. It knocked a huge amount of material into space, fragments of the crust and mantle of both planets. These fragments formed a disk around Earth. From this disk, under the influence of gravity, the moon began to assemble. Initially, it was a molten ball, a magmatic ocean. The entire moon was liquid. Then it began to cool. Lighter minerals floated to the surface, forming the crust. Heavier ones settled deep, forming the mantle and core. The crystallization process went on for millions of years. And here is the key moment. The moon cooled unevenly. One side of it faced Earth, hot, glowing, having just survived a catastrophic impact. Earth radiated heat, powerful infrared radiation, like from a giant oven. The visible side of the moon received an additional dose of heat from Earth, so it cooled more slowly. The far side, directed into cold space, cooled faster. What happens when magma cools faster? The crust becomes thicker. When it cools more slowly, it becomes thinner. It is like pouring water into two molds and putting one in the freezer and the other in the refrigerator. In the freezer, the ice will be thicker. On the far side of the moon, the crystallization process was more active. A thicker primary crust formed there. On the visible side, warmed by Earth's heat, the crust was thinner. And when volcanic processes began later, it was easier for magma to break through this thin crust. That is why the visible side is flooded with lava and the far side is not. It is all about the asymmetric cooling of the young moon under the gaze of the glowing Earth. But that is not all. There is another factor that intensified the asymmetry: the distribution of radioactive elements. Uranium, thorium, potassium, they decay, releasing heat. This heat supported the moon's volcanic activity for billions of years. It turned out that these elements are concentrated precisely on the visible side. How did that happen? The hypothesis is this: when the magmatic ocean was cooling, the last portions of the melt, the most enriched with incompatible elements that do not fit into the crystal lattices of minerals, ended up squeezed between the solidifying crust and the mantle, and Earth's tidal forces, constantly deforming the moon, drove this enriched material to the visible side. It concentrated there, creating pockets of long-lived heat. These very pockets fed the volcanoes that filled the impact basins with lava. It turns out the visible side of the moon is the result of two factors. First, a thinner crust due to slowed cooling under Earth's heat. Second, a concentration of radioactive elements supporting volcanism. The far side is deprived of both advantages. It has a thick crust and few heat sources. Therefore, it remained ancient, untouched, and covered with the scars of bombardments. And these scars tell a story. The far side of the moon is an archive, a time capsule preserving traces of events that were erased on the visible side by lava flows. Every crater is a record of an impact. Large craters are traces of catastrophic collisions. Small ones are marks from fragments flying through the solar system for billions of years. Layers of craters overlap each other like pages of a book. Reading them, scientists reconstruct the history of the early solar system, when planets were just forming, when orbits had not yet stabilized, and when space was full of debris and chaos. One of the most interesting regions of the far side is the South Pole Aitken Basin. This is a basin, but not just any basin. It is the largest impact structure in the entire solar system. The diameter is 2,500 kilometers. The depth is 13 kilometers. Imagine standing at the bottom of this depression and looking at walls rising 13 kilometers up. This is higher than Everest, and horizontally the distance is like from Moscow to London. A giant scar inflicted by the impact of an asteroid tens, or maybe hundreds, of kilometers in size. The impact occurred approximately 4 billion years ago during the late heavy bombardment era, a time when the inner part of the solar system was shelled by a swarm of asteroids and comets from outer regions. What is interesting is that in the South Pole Aitken Basin, the impact was so powerful that it pierced the crust completely and exposed the moon's mantle. The bottom of the basin is not crust. It is material from the depths. Composition analysis showed it contains a lot of olivine and pyroxene, minerals characteristic of the mantle. This is a unique opportunity to study the inner structure of the moon without drilling boreholes. The impact did all the work for us. Moreover, in the ejecta from the South Pole Aitken Basin, unusual element ratios were found. Thorium, which usually concentrates in the crust, is present there in small amounts. Iron, conversely, is in excess. This confirms we are looking at mantle material. But the South Pole Aitken Basin is interesting not only to geologists. It is a strategic location. The basin is located at the moon's south pole, and the moon's poles are special zones. There are craters there that are never illuminated by the sun. Eternal darkness. Why? Because the moon's rotation axis is almost perpendicular to its orbital plane. The tilt is only 1.5 degrees. On Earth, the tilt is 23.5 degrees, which gives us the change of seasons and the difference in illumination between the poles and the equator. On the moon, there is no such thing. Sunlight falls almost horizontally at the poles, and if a crater is deep enough, its bottom will never see light. These eternally shadowed regions are cold traps. The temperature there drops to minus 230 degrees. Nothing evaporates at such a temperature, and here is what was found there. Ice, water ice. Where does water on the moon come from? The moon is devoid of an atmosphere. Water should evaporate and be carried away into space. But in these cold traps, it remains. Where did it come from? There are two main hypotheses. First, comets. For billions of years, the moon was bombarded not only by asteroids but also by comets, icy blocks coming from the outer regions of the solar system. When a comet crashes into the moon, the ice evaporates from the impact. Steam scatters in all directions. Most of it goes into space. Some part, falling into an eternally shadowed crater, freezes and stays there forever. Thus, impact after impact over millions of years, a supply accumulates. The second hypothesis is the solar wind, a stream of protons that the sun ejects into space. Protons are hydrogen nuclei. When they hit the surface of the moon, they can interact with oxygen in lunar minerals, forming water. This is not liquid water, but molecules bound to regolith particles. But if these particles fall into a cold trap, water accumulates. The process is slow, but over billions of years, it can yield a significant result. Both hypotheses are likely correct. The ice at the moon's poles has a combined origin, and there is more of it than previously thought. The mission of the Indian probe Chandrayaan-1 in 2008 confirmed the presence of water ice in polar craters. The American Lunar Reconnaissance Orbiter mapped these areas. Estimates of the reserves vary, but they speak of hundreds of millions of tons of ice. This is a huge resource. Water on the moon is not just a scientific curiosity, it is fuel, it is oxygen, it is life. If you decompose water by electrolysis, you get hydrogen and oxygen, components of rocket fuel. One can refuel ships right on the moon without dragging fuel from Earth. This makes the moon not a final destination, but a transfer base, a springboard for flights further to Mars, to asteroids, into deep space. And here, the far side of the moon becomes key. The South Pole Aitken Basin is not just a place for scientific research, it is a potential site for the first lunar base. There is water, there are minerals, rare earth elements, titanium, and helium-3. Helium-3 is particularly interesting. This is an isotope that is extremely rare on Earth but relatively abundant on the Moon. Why? Because the Sun produces helium-3 and ejects it with the solar wind. This stream of particles has been bombarding the Moon's surface for billions of years, settling in the regolith. On Earth, the atmosphere and magnetic field protect us from the solar wind. Helium-3 does not reach the surface. On the Moon, there is no protection. The regolith absorbs it like a sponge. Why is helium-3 needed? It is an ideal fuel for the fusion reactors of the future. The fusion reaction of helium-3 with deuterium yields a huge amount of energy and produces almost no radioactive waste. The problem is that there is almost no helium-3 on Earth. It has to be produced in nuclear reactors, which is expensive and difficult. On the Moon, it can be mined. Estimates show that the upper layer of lunar regolith contains several million tons of helium-3. Just a few hundred tons could provide energy for the entire human civilization for a year. Of course, fusion technology using helium-3 is not yet perfected. We do not yet know how to conduct such reactions stably, but if we learn, the Moon will become humanity's energy warehouse. And once again, the far side is in the spotlight. Why? Because there are fewer lava seas there. Seas are basalt, a dark rock poor in helium-3. Highlands are anorthosites, light ancient crust rich in this isotope. The far side of the Moon is all highlands, meaning the concentration of helium-3 is higher there. Mining it there is more efficient. But there is another reason why the far side is important. And this reason is not related to geology or resources. It is silence. Absolute radio silence. On Earth, we are surrounded by radio noise. Cellular networks, television, radio stations, satellites. All this hum fills the electromagnetic spectrum. Even in the most remote corners of the planet, catching a signal from distant cosmic objects is difficult. Our own noise drowns them out. Radio astronomers fight this, building observatories in deserts, in mountains, in Antarctica. But there is no complete silence anywhere on Earth. The far side of the Moon is the only place in the vicinity of our planet where there is full protection from Earth's radio noise. The Moon itself shields the signals. 3,500 kilometers of rock block all radiation from Earth. If you put a radio telescope on the far side, it will hear only space. No interference. It is an ideal observatory for studying the weakest signals in the universe. What signals? For example, radiation from the first stars. After the Big Bang, the universe was filled with hot plasma. Then it cooled. The recombination era arrived. Electrons and protons combined into hydrogen atoms. The universe became transparent, but there were no stars yet. This time is called the Dark Ages, from 380,000 years after the Big Bang until the appearance of the first stars, approximately 100 to 200 million years later. Then the first luminaries lit up, and their ultraviolet radiation began to ionize the hydrogen around them. This is called the epoch of reionization. We want to study this period. It is key to understanding the formation of galaxies, but the signals from there are extremely weak and shifted into the long-wave radio part of the spectrum due to the expansion of the universe. On Earth, catching them is almost impossible. The ionosphere and radio noise interfere. On the far side of the Moon, it is possible. There are projects for lunar radio telescopes. One of them is to deploy an antenna array several kilometers in diameter in a crater on the far side. Thousands of small antennas working as a single instrument. They will listen to low-frequency radio radiation that carries information about the early universe, the first stars, and dark matter. Such a telescope could detect signals that we will never see from Earth. But to work on the far side, infrastructure is needed. How to control devices if there is no direct connection to Earth? Relay satellites are needed. China understood this and was the first to do it. In 2018, they launched the Queqiao satellite, a relay that hung at the Lagrange point of the Earth-Moon system. This point is behind the Moon but slightly to the side, so the satellite sees both Earth and the far side of the Moon simultaneously. It transmits signals between them. This opened the way for landing missions. On January 3, 2019, the Chinese station Chang'e 4 made the first soft landing in history on the far side of the Moon. The landing site was Von Karman Crater, located inside the South Pole Aitken Basin. The station landed, deployed panels, released the small Yutu-2 rover, and began working. It was a historical moment. For the first time, humanity touched that part of the Moon that had not been seen for billions of years. Chang'e 4 studied the soil. The rover drove across the bottom of the crater, analyzing the rock composition. The results confirmed that the material there differs from the visible side. There are more mantle minerals. This means that the South Pole Aitken Basin indeed exposed the deep layers. The station also studied the radiation environment. There is no magnetic field on the Moon. The surface is open to cosmic rays. Understanding the radiation level is important for future manned missions. Additionally, Chang'e 4 conducted a biological experiment. In a special container, they tried to grow plants. Cotton seeds sprouted, becoming the first living organisms on the far side of the Moon. True, they did not survive long. A lunar night lasts 14 Earth days, and without heating, the container froze. No, the fact remains. Life touched the far side. The success of Chang'e 4 showed that the far side of the Moon is accessible. It is no longer terra incognita. China did not stop. Chang'e 5 delivered soil samples from the visible side. Chang'e 6 is planned to deliver soil from the far side, the first return of material from there. This will allow for a detailed study of the ancient crust's composition and a refinement of moon formation models. And then, manned missions. China announced plans to land taikonauts on the Moon by the end of the 2030s. One of the goals is exploring the far side. But it is not only China that is aimed there. The United States, with the Artemis program, plans to return to the Moon. The target is the South Pole, where part of the South Pole Aitken Basin is located. The European Space Agency talks about a lunar village, an international base that could be built at the pole. Russia and China discuss a joint lunar program. India, having launched Chandrayaan-3, plans its own lunar station. Even private companies like SpaceX and Blue Origin look at the Moon as a market. Cargo missions, equipment delivery, tourism. The Moon, from a symbol of the Cold War, is turning into an arena for a new space race. But this time the race is not for flags, but for resources and strategic positions. And the far side is the prize of this race. Why exactly it? Because everything most interesting is there. The South Pole Aitken Basin with its mantle rocks and ice reserves, highlands rich in helium-3, radio silence for astronomy. This is not just a geological curiosity. It is a key to humanity's future in space. Now let us stop for a minute and think about myths. The far side of the Moon is surrounded by legends. The dark side, as it is often incorrectly called. Dark not because there is no light there. The sun illuminates the far side just as it does the visible one. We simply do not see it. Dark in the sense of unknown, hidden. And this unknown gave birth to fantasies. Alien bases, secret missions, artifacts of ancient civilizations. The internet is full of conspiracy theories. Supposedly, NASA hides photographs of alien structures on the far side. Supposedly, Apollo missions saw something there, but the information is classified. Let us figure out where these ideas came from. Firstly, from ignorance. When people do not understand why one side of the Moon is hidden, they start to think it is on purpose. Someone is hiding the truth. Secondly, from the fear of the unknown. Space is frightening. It is huge, cold, and indifferent. It is easier to imagine that someone is there, aliens, gods, anyone, than to admit we are alone in this void. Thirdly, from distrust of authorities. If a government can hide one secret, why can it not hide another? The moon landing, according to conspiracy theorists, was faked. This means photographs of the far side could also be fake, but facts are stubborn. The far side of the moon has been photographed by dozens of missions: Soviet, American, Chinese, Japanese, European, and Indian. All of them show the same thing: craters, basins, highlands. No pyramids, bases, or ruins. The resolution of modern images is so high that objects smaller than a meter can be made out. If there were something artificial there, we would see it. We do not see it because there is nothing there. Of course, there will always be those who say, what if they are hiding it? What if all the agencies agreed to stay silent? This is logically possible, but extremely unlikely. Space agencies of different countries compete rather than cooperate in conspiracies. China would gladly reveal an American secret if there were one. The United States would also gladly reveal a Chinese one. But this does not happen because there is nothing to reveal. What about strange objects in photographs? Sometimes on images of the far side, unusual shapes are seen. Square craters, straight lines, bright spots. Conspiracy theorists cry, "Here is proof." In fact, these are optical illusions, shooting artifacts, or simply unusual but natural geology. Square craters are the result of an impact occurring in a zone of tectonic faults, and the crater shape adapted to the crust's structure. Straight lines are chains of secondary craters formed by ejecta from large impacts. Bright spots are fresh craters with ejecta rays that have not yet darkened from space weathering. The moon is a museum of natural history. Every stone, every crater, every crack tells about the past. And on the far side, this museum is preserved best of all because there was no volcanic activity that would have erased ancient traces. No, it is a museum of nature, not of artifacts of intelligent beings. It is interesting that the very idea of the dark side of the moon has taken root in mass culture. The album by Pink Floyd, The Dark Side of the Moon, is one of the most famous in rock history. The title is symbolic. It is not about the moon, but about the dark side of human nature: madness, greed, fear. But the metaphor worked. The dark side is what we do not see, but it exists. What affects us, but remains hidden. And the moon with its invisible half is perfectly suited for this metaphor. Cinema did not stay on the sidelines either. The film Transformers 3 used the far side of the moon as a crash site for an alien ship. The film Iron Sky, a satirical science fiction about a Nazi base on the moon, series, books, comics, everywhere the far side serves as a backdrop for secrets. This is a cultural phenomenon. We project our fears and hopes onto it because it is the last place close to us that remained inaccessible for a long time. But what is truly amazing is that reality is more interesting than fiction. One does not need to invent aliens for the far side of the moon to be exciting. It is enough to understand what is actually there. A giant basin that pierced the crust to the mantle, ice preserving water that is older than humanity, silence in which the echo of the universe's birth can be heard, rocks that remember how the solar system was forming. This is not fiction, it is reality, and it stuns the imagination more than any invention. Let us now talk about how the far side of the moon changes our understanding of space. The moon is not just a satellite of Earth. It is our natural experiment, an open-air laboratory. By studying the moon, we learn to read the history of planets. Every crater is a lesson on how bombardment works. Every volcanic flow is a lesson on the internal heat of celestial bodies. Every anomaly is a hint of processes we do not yet fully understand. One such anomaly is magnetic fields. The moon currently has no global magnetic field, but there are local magnetic anomalies in its crust, areas where rocks are magnetized. Where from? The hypothesis is this: billions of years ago, the moon had a dynamo, a liquid core that rotated and generated a magnetic field like Earth's. Then the core cooled, the dynamo turned off, and the field disappeared. But some rocks managed to become magnetized while the field existed, and these magnetized areas have been preserved. On the far side, there are many such anomalies. Why exactly there? Perhaps the impacts that created large basins on the visible side demagnetized the rocks. High temperature during impact destroyed the magnetism. On the far side, there are fewer large impacts in lava regions, so magnetic traces are better preserved. These anomalies are important not only for the moon's history. They help understand how dynamos work in celestial bodies. Mercury, Earth, Jupiter, Saturn all have magnetic fields. Mars and Venus do not, but perhaps had them in the past. The moon is an intermediate case. It had a field, but it disappeared. By studying the remnant magnetism of lunar rocks, we model processes in other worlds. Another mystery of the far side is mass asymmetry. The moon is not an ideally symmetrical sphere. Its center of mass is shifted relative to the geometric center by about 2 kilometers toward Earth. Why? One of the reasons is mascons, areas of increased density hidden under the lunar surface. The name comes from the English mass concentration. Mascons are found under large impact basins. When an asteroid crashes into the moon, it creates a depression. Then this depression is filled with dense basaltic lava. Basalt is heavier than the surrounding crust. A local excess mass, a mascon, results. Most mascons are on the visible side because there are more lava seas there. No, there are some on the far side as well. Under the South Pole Aitken Basin, for example. These mascons affect the orbits of satellites. If a probe flies low over the moon, gravitational anomalies pull it and change its trajectory. This must be considered when planning missions. Mascons also tell about the internal structure of the moon. By analyzing their distribution, scientists model crust thickness, mantle density, and core size. It turned out that the moon has a small metallic core with a diameter of about 500 kilometers. This is roughly a quarter of the moon's radius. The core is partially liquid. This was confirmed by seismic data from instruments left by Apollo missions. Moonquakes, though rare, are registered. By analyzing seismic waves, scientists peeked into the depths. A solid crust, a viscous mantle, a liquid outer core, and possibly a solid inner core. The structure is similar to Earth's, but in miniature. And this structure formed from material ejected during the giant collision of Earth with the protoplanet Theia. That is the name of the hypothetical body that crashed into our planet 4.5 billion years ago. Theia is the key to understanding the moon. Modeling shows the collision was oblique, at an angle. Theia hit Earth not head-on, but glancingly. This knocked out a huge amount of material, but did not destroy Earth. The fragments formed a disk from which the moon condensed. Moreover, the disk was hot. The temperature was 1,000 degrees. The moon was born molten. And here is an interesting point. The moon's material is a mixture of Earth and Theia material. Analysis of the isotopic composition of lunar rocks showed that it is almost identical to Earth's. This is strange. If Theia were an independent protoplanet, it should have had a different isotopic composition. After all, different parts of the solar system's protoplanetary disk had different compositions. No, the moon and Earth are isotopically close. Why? There are several explanations. First, Theia formed in the same region of the solar system as Earth, therefore having a similar composition. Second, after the impact, the material of Earth and Theia mixed so strongly that differences were erased. Third, the impact was so powerful that it evaporated a significant part of the material, and from this steam both Earth and the moon condensed, therefore becoming similar. The exact answer is yet to be found. Samples from the far side of the moon, especially from the South Pole Aitken Basin, can provide new information. There is mantle material there that could have preserved traces of the primary composition. Another topic that cannot be bypassed is the future development of the moon. The far side is at the center of plans. Why? Because it offers what is not on the visible side: resources and strategic position. Water in polar craters is life. Without water, a long-term human presence on the moon is impossible. Carrying water from Earth is insanely expensive. Every kilogram of cargo to lunar orbit costs $1,000. If water exists on site, it can be mined, purified, and used. To drink, to grow plants, to produce fuel. This changes the economics of lunar missions. Helium-3 is the energy of the future. If fusion using helium-3 becomes reality, the moon will turn into an energy source for all of human civilization. Mining helium-3 will require processing huge volumes of regolith. The soil needs to be heated to high temperatures to release the trapped gas. These are industrial scales: bases, factories, transport. The far side, with its highlands rich in helium-3, will become an industrial center. Radio astronomy is science. A telescope on the far side of the moon will provide a breakthrough in understanding the universe. We will be able to listen to signals that are currently drowned out by Earth's noise. We will find traces of the first stars and understand how the first galaxies formed. Perhaps we will detect signals from exoplanets if there are civilizations there that emit in the radio range. This is a chance to answer the question, are we alone in the universe? No, developing the far side is a challenge. There is no direct connection to Earth. Relays are needed. China has shown that it is possible. Queqiao is working, but for a full-fledged base, a network of satellites is needed. At least 2, better 4, to ensure constant communication. These are infrastructure costs. Additionally, energy. On the moon, a day lasts 14 Earth days, followed by 14 days of night. Solar panels work only during the day. At night, other sources are needed: nuclear reactors, fuel cells, batteries. At the poles, the situation is better. There are peaks of eternal light where the sun almost never sets. No, these are rare points. There will be competition for them. Another problem is radiation. On the moon, there is no atmosphere and no magnetic field. Cosmic rays and solar radiation bombard the surface without obstacles. Long-term stay is dangerous for health. Protection is needed. Thick walls, perhaps using lunar regolith as a shield. Building bases underground in lava tubes, tunnels formed by ancient lava flows. Such tubes have been discovered on the moon, some with diameters of tens of meters. These are natural shelters, ready-made rooms. True, there are fewer lava tubes on the far side because there is little volcanic activity there. No, in the South Pole Aitken Basin, there are possibly traces of ancient volcanic activity there. Psychology is also important. Living on the far side of the moon is isolation. Earth is not visible in the sky, only stars and the sun. Communication with home via satellites has a delay of several seconds. In case of an accident, help from Earth will arrive in days. This requires special training and a special mindset. The astronauts who go there must be prepared for loneliness and autonomy. No, challenges do not stop us. Humanity has always strived beyond the horizon. We crossed oceans, conquered poles, went into space. The moon is the next step, and the far side of the moon is a step into the unknown that is becoming known. Every mission there is not just a scientific achievement, it is a statement. We can. We are capable of reaching a place that was inaccessible for the entire history of civilization. And not just to reach, but to stay and work and build. The Chinese Chang'e program plans a series of missions to the far side. Chang'e 6 will deliver soil samples. Chang'e 7 will study the resources of the South Pole. Chang'e 8 will test technologies for using local materials, building from lunar regolith and mining water. These are steps toward a permanent base. The United States Artemis program is also aimed at the pole. Landing modules, rovers, manned missions. The European Space Agency is developing modules for a lunar village, a concept for an international base. Russia talks about a lunar station. India plans its program. All this converges at one point: the moon, and especially its far side is becoming an arena of activity. And here is what is important to understand. This is not a repetition of the space race of the 60s. Back then, the goal was symbolic. A flag on the moon, proof of superiority. Now the goal is practical. Resources, science, positions. The moon is viewed as a bridgehead for further expansion. A flight to Mars is easier to start from the moon than from Earth. Less gravity. One can refuel with water and fuel produced on site. Asteroids, potential sources of metals and rare elements, are closer to the moon than to Earth in terms of energy costs for flight. The moon is the transport hub of the solar system, and the far side is a quiet harbor, a place where one can work without interfering with or being influenced by Earth. Radio astronomers will be able to listen to space without interference. Biologists will be able to set experiments in conditions impossible on Earth. Low gravity, vacuum, extreme temperatures. Geologists will study the history of the solar system, reading the records in the stones. Engineers will test technologies that will then be used on Mars and beyond. It is a scientific and technical laboratory on a planetary scale. Now, there is also an ethical question. To whom does the moon belong? The Outer Space Treaty of 1967 states, "Space, including the moon and other celestial bodies, is not subject to national appropriation. No country can declare the moon its territory." No, the treaty does not prohibit the use of resources, and here the gray zone begins. If a company or a country builds a base on the moon and starts mining helium-3 or water, to whom do these resources belong? To the one who mined them, or to all of humanity? Legislation lags behind technology. The United States passed a law allowing private companies to own resources mined in space. Luxembourg passed a similar law, but there is no international consensus. The far side of the moon could become a field of conflict if several countries claim the same polar craters with water. How to resolve the dispute? If one country sets up a radio telescope and another nearby starts industrial activity creating radio interference, who is right? New international agreements are needed. The moon must remain a common heritage, not turn into an arena for conflicts. This is a lesson of history. Antarctica was divided without wars, thanks to a treaty that made it a scientific territory. The moon deserves the same. Let us look at the far side of the moon through the eyes of a philosopher. What does it symbolize? It is a place that has always existed but was invisible. Half of reality that we did not notice. And now we have finally looked there. What does this say about human knowledge? That there is always a far side. Always what we do not see, do not know, do not understand. No, this does not mean it is inaccessible. It means one must make an effort, find a way, invent a tool. Luna 3 is a metaphor for the scientific method. We cannot see directly. Let us create a device that will see for us. We cannot reach. Let us build a rocket. We do not understand. Let us conduct an experiment. The far side of the moon also reminds us of our place in the universe. The moon is locked in synchronous rotation, a coincidence of gravity. No, this coincidence determined our entire history of observations. If the moon rotated faster or slower, we would see its entire surface. There would be no mystery of the far side, no myths. Perhaps there would be no incentive to explore it. Coincidence shapes culture. This is true not only for the moon. Our entire civilization is a product of coincidences. Earth is at the right distance from the sun. We have a moon stabilizing the rotation axis. We have a magnetic field protecting against radiation. We had the right sequence of evolutionary events. Coincidence after coincidence. And here we are. The far side of the moon is a reminder of this. Another thought. The far side is a metaphor for the future. The future is always hidden from us. We do not know what is there. We build plans, forecasts, models. No, reality always turns out to be different. When Luna 3 photographed the far side, scientists expected to see seas. They saw craters. The expectation did not match reality. So it is with the future of humanity. We build plans for exploring space. Now, what will we find there? What surprises await? Perhaps we will find traces of life on Mars. Perhaps we will find a way to communicate with other civilizations. Perhaps we will face dangers we did not suspect. The far side of the moon teaches, be ready for the unexpected. No, most importantly, the far side of the moon returns our sense of wonder. In a world where we know about every corner of Earth thanks to satellites and the internet, where any information is a click away, it is easy to lose the sense of mystery. Everything is known, everything is studied, but it is worth lifting an eye to the moon and remembering. There, beyond the horizon we do not see, lies a world we are just beginning to understand. A world where every stone is a story, every crater is an event, every shadow is an opportunity, and this world is waiting for us. Humanity stands on the threshold of a new era. The era of exploring Earth is over. We have mapped every continent, every ocean. The era of near-Earth space is open. We fly to orbit regularly. We have space stations. Now the interplanetary era begins. The moon is the first step, Mars the second. Asteroids, satellites of Jupiter and Saturn are further, and the far side of the moon is a symbol of this step. A place that was inaccessible becomes a home. A place that was frightening becomes familiar. And here it is important not to lose respect. The moon is not just a stone in the sky. It is part of our history. It rotated over the first people who looked at the stars. It shone for poets who wrote about love and death. It guided seafarers who discovered new lands. It inspired scientists who derived the laws of gravity and mechanics. The moon is part of us. And when we build bases on its surface, mine resources, and turn it into an industrial site, we must not forget about this. The moon deserves respect. The far side of the moon is special. It was hidden for so long. It preserved traces of the past that the visible side lost. It preserves a silence that exists nowhere else near Earth. When we come there, we need to remember, we are guests, we study, we use, but we do not own. The moon belongs to space, belongs to history, belongs to the future. Our task is to understand it, not destroy it. And when you think about it, you realize the far side of the moon is not just geography. It is a challenge to our curiosity. Will we be able to unravel its secrets? A challenge to our technologies. Will we be able to get there and work there? A challenge to our ethics. Will we be able to use resources without destroying what we study? A challenge to our unity. Will we be able to cooperate rather than compete? These are questions that the next generation will answer. Those who are now in schools and universities, who will build lunar bases, who will first step on the far side, who will first hear in a radio telescope a signal from the dark ages of the universe. The moon is waiting, the far side is waiting. It is no longer dark. We illuminated it with our cameras, our probes, our knowledge, but it is still mysterious because the more we learn, the more questions appear. Why is the asymmetry so strong? What processes formed the mantle? How much water is actually in the polar craters? Are there resources on the moon we do not even suspect? Can life exist in lava tubes protected from radiation? These are questions for which we will find answers only when we come there and start working. And when that happens, the far side of the moon will stop being the far side. It will become just a side and another part of our world. A world that is expanding every day. At first, we knew only our village, then our country, then the whole Earth. Now we are expanding the borders to the moon, to Mars, further, and the far side of the moon is the first page of a new chapter of this story, a chapter that will be written not by us, but by those who come after. No, the beginning has been made. Luna 3 took the first photo. Chang'e made the first step. What happens next depends on us. I want to end with this. When you next look at the moon, and it will be there, as it was for thousands of years, as it will be for thousands more, remember that what you see is only half. Beyond the horizon lies another world, a world of scars and silence, a world of ice and mantle rocks, a world that preserves the history of the solar system. And this world is no longer closed. We looked there, we touched it. Soon we will live there. The far side of the moon is not the end of the journey. It is the beginning of humanity's path to the stars. And each of us is part of this path. Everyone who looks at the moon with curiosity, who asks questions, who wants to know more. We are all researchers. We are all discoverers, because one can discover not only new lands, but also new ideas, new understandings, new dreams. The far side of the moon is a reminder. There is always something beyond the horizon. There is always a next step, and that step is worth taking. If you like this journey to the far side of the moon, give it a like and subscribe to the channel. There are still many secrets of space ahead that we will reveal together. See you in the next episode.